friends, I welcome you to my YouTube channel MacPM. So in this video we will try to derive a continuity equation in three-dimensional form, okay, which is in the form of differential equation. So suppose this is a control volume, this is the unit cube which is control volume. So we will conjure masses entering and exiting from this control volume. So what will be the mass entering through phase ABCD phase? What will be the mass entering? Okay, see, so in x direction velocity is u, in y direction it is v, in z direction it is w, okay, and dx is the length of the unit cube in x direction, dy in y direction, and dz in z direction. So mass entering the ABCD phase is mass is equal to rho AV, okay, mass flow rate rho AV. So rho is density, into A is area, into V is velocity. So in x direction, what is the area? Area of the phase AB CD is this length, which is dy, see here, and this length is equal to dz. So area is equal to dy dz. So mass will be equal to, from phase ABCD will be equal to mass flow rate from ABCD in x direction is equal to, see, rho density into velocity. Velocity in x direction is u, into area is dy dz, or you can also write it rho u dy dz, okay. So this is mass entering in x direction, okay. Similarly, mass entering in y direction will be equal to rho v in y direction. See, in y direction like this, this, so it will be dz into dx, rho v dx into dz. Similarly, in z direction it will be rho w dx dy, okay. So this is the mass entering from all the phases, three phases, okay. And what will be the mass exiting from this x direction? From phase, it is entering from ABCD, and it will exit from this phase in x direction. So what will be the mass exiting from x direction? It will be from phase AB EFGH. It will be equal to mass leaving in x direction phase EFGH. So what will be it? So there will be change in density with respect to x. So density will become rho plus del rho by del x into dx. This will be new density because it is changed now. Then what else can change? See, from here u will change. So u plus del, it is a velocity in x direction, so del u by del x into dx. So this is the new velocity in x direction. And now area dy dz will be same, okay. So if we multiply these two, then you will get rho u plus rho del u by del x dx plus u del rho by del x into dx plus del rho into del u by del x square into dx square. So this is higher term, so dx is very small, so it is del x square is even smaller, so we'll neglect this, okay. So mass exiting in x direction is rho u plus rho del u by del x dx plus u del rho by So we can write it as del rho u by del x, okay, into dx. So this is into dy and dz. So this is mass exiting in x direction, okay. So similarly there will be mass exiting in y and z direction also. Okay, so in y direction it will be rho v plus del rho b by del y into dy into dy. In place of y it will become dx into dz. In z direction mass exit will be rho into w plus del rho w upon del z into dz into dx into dy. So this is mass exiting from the x and y and z direction, and rate of accumulation of mass will be equal to del m upon del t. Rate of change of mass in the control volume will be del m upon del t, which will be equal to del upon del t. Mass is equal to rho into dv, okay. So which is equal to del rho upon del t into dv, okay. Now what will be the total if we do the conservation of mass? Then what are the masses entering in this control volume? It was like this. See this one, rho u, we will write them, rho u dy dz plus rho v dx dz plus rho w dx dy is equal to mass accumulation del rho upon del t into dv plus this is rate of change of mass plus exit mass leaving from x direction is rho u. We will write these terms, rho u plus del rho u upon del x into dy dz plus in y direction rho v plus del rho v upon del y into dy dx dz, sorry, plus rho w plus del rho w upon del z into dz into dx dy. So we can write again, if you multiply dy dz here, then it will become rho u dy, or right side term we will again write it del rho upon del t dv plus rho u dy dz plus del rho u upon del x, this y dx into dx dy dz plus rho v into dx dz plus del rho v upon del y into dx dy dz plus this rho w into dx into dz plus del rho w upon del x into dz del z into dz into dx into dy. So if you see carefully, these terms are equal. Del if you see carefully, then these terms are equal. Rho u du dy dz and here also you can see rho u dy dz. So these will be cancelled, this will be cancelled, and this will be also cancelled. Okay, so from here you will get del rho upon del t, from here dv plus this one del rho u upon del x, and dx dy dz is common in everywhere, del u by del x plus this one del rho v upon del y plus del rho w upon del z into dx dy dz, okay, is equal to 0. So now dx dy dz can be written as volume, so del rho upon del t into dv plus del rho u upon del x plus del rho v upon del y plus del rho w upon del z. In this we can also take dv as outside, so dv is equal to 0. So this is our continuity equation. Okay, and if we can check dv is equal to 0, because these two things are 0, multiplication is 0, so either this can be 0 or this can be 0, so we can also write it as del rho upon del t plus del rho u upon del x plus del rho v upon del y plus del rho w upon del z is equal to 0. So this is also continuity equation, this is also our continuity equation. Okay, so this is the main form of continuity equation. Now depending on various type of flow, we can change the continuity equation or modify the continuity equation. Like this is the main continuity equation, equation number 1, general. Second, if fluid is steady flow, means there is no change in time with respect to time, then this term will become 0. Del rho upon del t will become 0. So del upon del x rho u plus del rho v upon del y plus del rho w upon del z is equal to 0. So this will be true for steady flow. Okay, and if there is this is incompressible flow, then density will become constant, so it will become 0. It will come out as common and it will become 0. Not 0 means it will come out, so it will become rho del u upon del x. We will take common because density is constant, so it will come out of the derivation, plus del v upon del y plus del w upon del z is equal to 0. So from here del u upon del x plus del v upon del y plus del w upon del z is equal to 0. So this is continuity equation for incompressible and steady flow. Okay, see, so this is our final continuity, very simplified continuity equation, and if it is in 2 dimension, then it will become del u upon del x plus del u upon del y is equal to 0. So this is for 2 dimension incompressible and steady flow. Okay, so I hope you understood how to derive the continuity equation. This is very important equation in the fluid mechanics. You will use it everywhere. Okay, so if you like this video, then please share and subscribe to our channel, and thank you for watching.